Hello, so going to read another paper. It seems very interesting. Once again, Mistral as our help. Mistral is at our service, so let's do it. So, this paper is called a hybrid approach combining deep learning and signal processing for bearing fault diagnosis under imbalanced samples and multiple operating conditions. So, sir, they're doing fault diagnosis under imbalance samples. So, probably it means some classes has more samples, some classes has less samples, way less or way more, and multiple operating conditions. Okay, we are gonna summarize it with Mistral. Ah, so let's see. So this paper presents a hybrid approach for bearing fault diagnosis that combines deep learning and signal processing techniques to address challenges such as imbalanced samples and multiple operating conditions. Okay, so it introduces a novel framework that integrates GANs, transform learning, wavelet transform, which from signal processing, asymmetric convolution networks, and multi-hand attention mechanisms. So how they're tackling the imbalance sample issue? They're using GANs to generate synthetic fault data, augmenting the dataset and improving model generation. So obviously fault, yeah, and to handle multiple operating conditions, they're using transfer learning. So enables the model to adapt to different operating environments with minimal target domain data. Yeah, interesting. And then we have time frequency representation. The use of continuous wavelet transforms to convert vibration signals into time frequency representations is a significant contribution. Okay, I have to look into it. This allows the model to capture both temporal and frequency domain features, which are crucial for diagnosing non-stationary fault signals. So, asymmetric convolutional networks. The paper proposes an asymmetric convolutional network with multi-head attention mechanism to improve feature extraction. The asymmetric kernel enabled the model to capture local and global relationships more effectively, enhancing the accuracy. Transfer learning from domain adaptation. We've seen this before. Uh, from source domain to a target domain with only 10% of the target data. Okay. Experimental validation. The method is validated using two widely recognized datasets, Paderborn and CWRU. So CWRU stands for Case Western Reserve University. So once again, let's look at the methods applied in a little more detail. GANs are used to generate synthetic bearing fault data, addressing the issue of imbalance samples. This synthetic data is combined with the original data to create a more robust training set. And it also discusses the challenges from overfitting with synthetic data and proposes regularization techniques to drop out early stopping to mitigate this issue. Then we have wavelet transform. The CWT is employed to convert 1D vibration signals into 2D time frequency spectrograms. This transformation helps in capturing the temporal evolution of frequency components, which is essential for fault diagnosis. Then we have ACNet, which is asymmetric convolution kernels 3 times 3, 1 times 3, 3 times 1 to extract features more flexibly and efficiently compared to traditional kernels. The multi-head attention mechanism is integrated into the ACNet to focus on key areas of the time frequency representations enhancing feature fusion and interpretability. Okay. Then we have the transfer learning. Transfer learning is used to adapt the model to different operating conditions. The model is pre-trained on the source domain and fine-tuned on the target domain using a small subset of data. This approach reduces the need for large level datasets in the target domain. Evaluation metrics. The paper evaluates the model's performance using metrics such as. So we are looking at evaluation metrics. F1 score, accuracy, confusion metrics. Visualizations like t-SNE are also used. And implication, results and implication. So fault detection, high accuracy in fault detection and classification on both the Paderborn and CWRU datasets. So let's take a look from Kaggle about the CWRU bearing dataset. So there are few the context. There are few datasets on mechanical engineering, in particular devoted to apply machine learning in industrial environment. So this data is provided to Kaggle by Case Western Bearing Data Center. The contents are motor with 2 HP power, torque transducer, dynamometer, control electronics. This is the test bench. The test bearings support the motor shaft. Defects were introduced at a single point by EDM machining. The diameters of defects in inches, millimeters, 0.007, 0.014, 0.021. There is a time series for each defect located in one of 3 parts of the bearing: ball, inner race and outer race. Telemetry measurements come from 3 accelerometer installed on 3 positions in the system: drive end, fan end and base. Dataset corresponds to the following conditions: 1 HP load applied to the motor, shaft rotating speed 1772 rotation per minute, 48 kilohertz sampling frequency of the accelerometers. So features important. 9 features are calculated. Maximum for fault identification prediction, maximum, minimum, mean, standard deviation, RMS, skewness, kurtosis, crest factor and form factor. Each feature is computed for time segments of 2048 points. There is 0.04 seconds at the 48 kilohertz accelerometer sampling. Alright, so we have 9 features. That's the key thing. Let's go back. So they also discuss about robustness to imbalanced data and real-time applicability, which is this is interesting that the model is expected to run in 0.15 milliseconds on a CPU platform, making it suitable for industrial applications. Future research, lack of interpretability, limitations of DL models, computational cost of training and inference, explainable AI techniques to improve model transparency, incorporating techniques like online learning and adaptive transfer learning could enhance. Alright, so this is the paper for you. The interesting part is the integration of generative adversarial networks, wavelet transform, asymmetric convolution networks, multi-head mechanism. So yeah, they're bringing in some techniques from both deep learning and signal processing to solve a problem which is roughly mainly for fault diagnosis in mechanical engineering domain. One can say that. So yeah, I probably will do some follow-up questions. So that's what we have here. Peace.